Good morning, students. Today we go for another lesson on FET amplifiers. In last lesson, we have learned common source FET amplifier, which is equivalent to common emitter FET amplifier, BJT amplifier, and these are the two most common configurations. There are other configurations, other two, which are not so popular, but we should know their usage. One is I'll go by this common gate, which is equivalent to common base in BJT. In common gate amplifier, what you should notice, it is the same components and same arrangement of the common source amplifier. I'll show the common source amplifier was this. There was a drain resistance, source resistance, biasing two resistances, and there is a coupling, a bypass capacitor of the resistance which is connected to the source. And there are coupling capacitors and load resistances, etc. Forget about them. So now I go to common source common gate amplifier. Here you see the same FET, which is just connected differently. This is the power supply, and this is the drain resistance. I'll take the pointer. This is the power supply. This is the drain resistance, current flowing through the drain, and current flowing through the source. And this is the source resistance connected to common. So this line, you will agree with me, remains same as the common source amplifier. These are the two bias resistances, R1, R2. Also, you should agree they remain same. This is a load coupling capacitor. This is a source and the source coupling capacitor. The bypass capacitor now is connected through this line, because the bypass capacitor always has to be in the line of my signal current or signal potential, signal Kirchhoff's loop. This is a signal Kirchhoff's loop, and bypass capacitor has to be here. So really there is nothing new what I can explain you about this amplifier. The design procedure, values of the resistances, capacitors all remain same. So the structure is same as a common source amplifier. Fine. But only difference is input is given to the source. Earlier, input was given to the gate from this side. Now it is given from this side, but the loop remains same, right? This is a common drain source follower, which is equivalent to BJT common drain emitter follower. Here, what you see, there is no drain resistance RD. That means there is no resistance between the power supply and the drain. Like here is a resistance between power supply and the drain. Here there is no. As a result, what happens? When signal current flows through this, whatever very small current is concerned, and the signal current potential appears here, and there is a varying signal current in this line. This varying signal current is shorted to common in this line through the DC power supply. Because you remember I told a number of times any DC supply is actually a short circuit for AC supply. So this IDSQ is the DC current, which will be superimposed by the varying signal current, and that will be short circuited to the common. And that is why it is called common drain. If you look at the circuit, often students get confused. The drain is connected to power supply. Why it is common drain? but it is common for the signal, so far as the signal current is concerned. And there is a load, coupling capacitor, source, coupling capacitor as usual. Only this biasing part is little different. Here, there was a source resistance, RS. Here, source resistance is divided into two parts, RS1 and RS2. And calculation is done in such a way, the potential drop across RS1 provides the necessary potential difference between the source and the gate. And there is a resistance R1 which is used for the providing the bias. Output is taken from the source. Here, output is taken from the source, right? Output is taken from the source, and a potential drop IDS to RS1. This potential drop, since it is connected from here to here, then what is the potential difference between this point and this point? It is a potential drop across RS1. So in your design, if you have designed IDSQ like we had designed at 3.5 milliampere, so 3.5 milliampere multiplied by this RS1 will provide the necessary potential gap here, which in our design is minus 0.6 volt. So that is all, right? So these are the two configurations of common gate and common drain. We can now go for testing these two configurations, right? So we shall go out of here and I'll change the screen. It will take a few seconds. I'll change the screen and now you have the new screen. This is the common gate amplifier. See, this is the FET and this is the R2 and this is RS, and this voltmeter I have connected here to check that VGS bias at minus 0.6 volt is okay, and IDS bias of 3.5 milliampere is also okay. And these are the same resistances, same load resistance, power supply. So I really don't have to give you anything new here. Only as a routine, I need to show you how this amplifier works. Here, once again, if I run this amplifier, the blue line is the input and the red line is the output. Fine? And if you, similar way, you connect a voltage probe at the input, another voltage probe at the output, and find out their values. The peak-to-peak output is 2.97 volt and peak-to-peak input is 848 millivolt. That gives a gain of 3.5. So once again, as I said, FET amplifier purpose is not gain, but to provide high input impedance, right? So if I close this and then I show you the distortion and the frequency plot. This is the frequency plot and this is the distortion. Run it once again. Like common source, here also the distortion is very slow, very low, about 4.7% distortion, and gain here. And here, gain we have already found 3.5 in linear scale. And let's see what is the lower cutoff frequency. Here the gain shows is 11.738 dB and minus 3 dB point will be 8.738 dB. So 0.738, 8.738, here 8.624, here 8.894. It will be somewhere in between them. So it is something around 15 hertz, the lower cutoff frequency. I repeat once again, that is the beauty of FET amplifiers. Yeah, its low frequency gain. A low frequency gain is very, very good. Very, very good distortion, bus voice of the low frequency amplifier. So that was a common gate amplifier. Let us see now the common drain amplifier. This common drain amplifier, like common collector amplifier, is called emitter follower. This is called source follower. The same, this RS has been divided into two parts, and when I calculated to provide minus points for the IDS of 3.5 milliampere multiplied by 180 ohm provides me around 600 millivolt, which is necessary between the gate and the source. Other components remain same. Here, like in a BJT common emitter follower, the gain is, there is no gain really. Here also there is, you will find there is hardly any gain. There is hardly any gain. I'll reverse the see. Red line is the output, red line is the output, blue line is the input. So actually output is less than the input. By measuring, it was found that the gain is 0.74. So common emitter follower in BJT is not used for gain, it is used for impedance matching. Similarly, common drain source follower is not used for gain, it is used for impedance matching, right? And here, impedance matching, here, if you measured the input current and input voltage, input current and input voltage, here what I find that current peak to peak is 27.3 microampere, voltage peak to peak is 848 millivolt. That makes an input impedance of 31 kilo. 31 kilo is a very good, of the order of high input impedance. So when you want an impedance matching in a cascade series, then sometimes towards the end, before power amplifier, you need an impedance matching. There you use this particular configuration. You don't get amplification, but you get your very, very high input impedance. And if I now run the frequency plot and distortion meter, here the distortion meter, distortion here is surprisingly zero. That means these are the nitty-gritties of various configurations you have to remember. This common BJT-based amplifiers have a distortion of 10 to 20%. FET-based amplifiers have a distortion of around 4 to 5%. And common drain FET amplifier has a distortion of zero, absolutely zero. Because here, the output is just following the input. If the input does not have any distortion, output will not have any distortion. Another very important point, see this particular both. There is no gain. There is no gain. Gain is minus 3 dB already. But higher cutoff point is almost infinity. That means if your signal frequency is very high, then if you use, then you can use this, if you can use this particular configuration and you get rid of any worries of higher frequency distortion. I'll show you. This is 10 megahertz maximum. If I make it even 100 megahertz, Even then, it remains flat. It remains flat. So the main common drain FET source follower is high input impedance, zero distortion, and very high upper cutoff frequencies. So these are the two configurations, last two configurations of FET. And I think I have finished the topic of FET amplifiers. Next day we shall go to the next topic.